Hello everybody, this is lecture 3 on units and error, and so today we're going to talk about units and error. We're going to talk about when we have quantities in numerical tools, about how to think about those quantities in terms of both their physical units and their data types, how computers store those numbers, and then how that storage leads to finite precision errors that we have to think about, that we might not have to consider in analytical mathematics. So the three things we're going to talk about today are, one, we're going to talk about units, and then two, we're going to talk about data types. And data types I'll define later, but data types are how computers store numbers. And then finally, three, we're going to talk about finite precision errors. Okay, and there are two activities associated with this. There's an Excel activity here for units, so an Excel activity on units, and there's a Python activity here on finite precision errors. Okay, so let's start with the first one, units. And since this is my first lecture video where I'm writing things out, I'd just like to apologize a little bit for my handwriting. It's a little bit hard to write on a computer, so I'm doing my best. Okay, so all physical equations have units. All physical quantities have units. It doesn't make sense to talk about a physical quantity without units. So if you want to think about how much you weigh or how fast you're going, you have to think about that in terms of a reference to some other physical dimension. So units are really just a standard reference. So units are a standard reference. Okay, so if I want to talk about how high I am, I might talk about how tall I am in feet or in meters. Okay, and these are just standard lengths that we've defined that we can then refer to and we have some idea about. Okay, usually we have to think about the different kind of dimensions that we might have for a reference, and these dimensions are things like length, time, mass, temperature. Okay, there can be a bunch of other things like magnetic strength, strength of magnetic field, etc. Okay, there are two main systems of units. Okay, the first is the SI unit system, the international system, and the second are English units. So you're probably already familiar with this. Hopefully you've used these kinds of units in high school. And for this class, part of the things that you're expected to know, part of the course outcomes that you need to know for the class have to do with units. And so I have defined 13 units that you need to be able to know and convert between without looking up. So these units, let me pull it up here, if I can find it. Here it is. I call these the big 13 units. Okay, so they have these following dimensions: time, length, mass, force, and temperature. Force is a derived unit. We don't really have to worry about that in class. All right, the difference between primary and secondary dimensions, but we'll talk about that in fluid mechanics if you ever take it from me. And here are the two different unit systems, SI and English, and you can see here seconds, hours, meters, feet, kilogram, pounds, slugs, etc., all the way down. All right, and here are the different unit conversions that you need to know, and you need to be able to do these unit conversions without looking up this worksheet. Okay, so for example, if we're going to convert between suppose I have 7 newtons and I want to know what that is in pounds force. I need to say, well, 7 newtons. I need to be able to convert 7 newtons multiplied by 1 pounds force is equal to 4.448 newtons. And if you go ahead and do that calculation out, that gives you 1.574 pounds force. Okay, so I trust that you've done unit conversions before, and you're going to get some practice on your homework, but this is part of the course outcome, so I'm just sort of highlighting it. So a couple other things to say about units really quickly before we finish this section. So first is this principle of what's called dimensional homogeneity. So dimensional homogeneity. Okay. Dimensional homogeneity is the concept that, I think I want to put a colon there instead of an equal sign. So all equations must have the same units on both sides. Okay, so an example of this is force equals mass times acceleration. Okay, over here I'm going to have, if I have say newtons, over here I'm going to have kilograms, and this is meters per second squared, but that's equal to a newton. Okay, so I have to have newtons equals newtons. So that's dimensional homogeneity, and all equations must obey this. So I can't have something where I have, mass equals time. That doesn't make any sense. How can I have something that's mass equals time? An equation must have both things on both sides be consistent, or they must be dimensionally homogeneous. Okay. So knowing this should help you to make sure when you're doing math that everything's right. Okay, so if you have equations on one side and equations on the other side, other side of the equation, and they don't have consistent units at some point, then you've made a mistake. Okay, so now what happens when we do computation with units, or computational tools with units? There are some tips, okay, that I'd like to give you, and I'm going to tell you these tips. And and it looks like I need a new page. Let me go ahead and add that in. Page, new page after. Okay. These tips maybe sound a little bit trumped up at this point to you, but hopefully you'll see the wisdom in them. So the tips are: first, pick a single unit system. Okay, so either SI or English units. Okay, pick one and stick with it. The second one will be convert at the beginning and end of your of your code or your sheet. Okay, so pick all of your quantities. So if you're given, say, a mass and a temperature and a time at the beginning, and you're given some other, some inconvenient units, do all the unit conversions at the beginning, and then do all of your conversions at the end, and don't do in the middle. It'll make your code a lot easier to follow. Okay, if you pick one spot, or just the beginning and end, 2 spots to do that. Okay. The third tip is use either kilograms, meters, and seconds, or slugs, feet, and seconds in your calculations. Okay, and the reason for this is that it's kind of hard to convert between. Well, it's easy in this case to convert between force and kilograms meters per second squared. Okay, because 1 newton is equal to 1 kilogram meter per second squared, and the same thing here. A pound's force is equal to 1 slug foot per second squared. We can see that if we come back and look at our unit conversions here. All right, but if I use pounds mass instead of slugs, I have to do this 32.17 conversion all over the place. Okay, and that's really a pain. All right, that will break this rule here of converting at the beginning and end of your code. So at the beginning, convert to slugs, and if at the end you need to know something in pounds mass, just do that 32 conversion at the very end. Okay, and then the last tip is use an absolute temperature scale. Okay, so that would be either Kelvin or Rankine, right? So if we come over here and look, we have this conversion between Kelvin and Rankine. So if you're given something in Fahrenheit, convert it over to Rankine. If you're given something in Celsius, convert it to Kelvin. Almost all of the things in engineering that we need to do, many of them need an absolute temperature scale. Some of them don't if you're taking differences, but if you convert to an absolute temperature scale at the beginning, you'll always be okay. All right, so that's what I'm going to say about units and my tips about units. So here now is a unit activity. Take a few minutes and stop and go do that activity and practice some unit conversions in Excel, okay? Okay, so having done that activity, now let's go on to the second thing we're going to talk about, which is data types. Okay, so this is our probably newest concept for the day, and this is to talk about how we store numbers in a computer. Okay, so variables must be stored in memory in a computer. Remember, we said the different parts of computer we had I/O. Remember, we had input, and then we had a CPU, and we had memory, and then we had output. And this was our computer. All right, so somehow the numbers need to be stored in memory. And memory is basically a bunch of ones and zeros, on and off states that are stored. And remember, there was volatile and non-volatile memory that lasted with and without power. And there are 4 different kinds of variables. So remember, a variable is just some quantity of memory. I said it's kind of like a thing of an ice cube tray, just one piece of an ice cube tray, right? We have to store some value here. Say we wanted to store the number, 4, okay? We would need some way to store the number 4 in ones and zeros, right? What is that going to be, we need ones and zeros somehow to store that. So there are 4 different kinds of ways to store things, okay? So we can have what are called Boolean variables. Okay, these are true and false values. We can have integers. Okay, these are your cardinal numbers like 1, 2, 3. Okay, or minus 4, something like that. Okay, there are strings or characters. Okay, these are things like A, or that's a character, or a word like book. Okay, that would be a string. Or it could be a number, but we just store the characters for the number, like 1, 2, 3. Okay, those are strings. And then the last thing is what we call a floating point number, which is a decimal. Okay, so decimal, aka a float. And we'll explain where float comes from in a minute. So that's things like 3.14159. All right. So in memory, at the end of the day, memory, we have to store all these things as ones and zeros. And just as an aside, okay, quick aside, in memory, we measure we have 1 bit that equals a single 1 or 0. Okay, we have 1 byte. While we're learning about units, here's units on a computer. Is 8 bits, right? A kilobyte, okay, is 1,000 bytes, all right? And then a megabyte is 10 to the 6 bytes, etc. Okay, and a gigabyte, is 10 to the 9. So gigabyte, that's 10 to the 9. Bytes, etc., etc. Okay, terabyte is 10 to the 12, and I think a petabyte is 10 to the 15. Okay, so that's just a little bit of background. We're going to use that when we talk about data types here in just a second. All right, so let's go through each of these guys really quick. Boolean, integers, strings, and decimal or floating point values and talk about how they're stored. So this is an important thing to try and remember. All right, this is one of the things you need to get out of the lecture today. So Boolean variables, okay, how are they stored? So a 0 is a false and a 1 is a true. So it's just a single bit. That's all we need in principle. Okay, 1 bit. I don't remember exactly in Python whether they only use 1 bit or not. Probably not. But in principle, all you need is 1 bit to store that. Okay, integers are next. Okay, so integers, you can store them as binary numbers. So for example, I can write the binary number 1011. Okay, and if you remember binary, hopefully you learned this in a math class somewhere along the way about binary numbers. But this is the 2 to the 0 place. This is the 2 to the 1 place. This is the 2 to the 2 place, right? And this is the 2 to the 3 place, right? Normally when we think about writing numbers base 10, that would be 10 to the 0s, 10 to the 1s, 10 to the 2s, and 10 to the 3s. That would be 1011. But if we want to convert this to decimal, we say 2 to the 0, so that'll be 1, plus 2 is 3, plus 8, so this is 8 plus 0 plus, I said that was 2 plus 1, so that's going to give us a value of 11. All right, so now this would be a number stored with 4 bits. So depending on how many bits you get depends on how large of an integer you can make. All right, so normally integers are given, say, maybe 2 bytes. Okay, and 2 bytes would give you around about 64,000 numbers. Okay, that you could come up with. You would need 1 bit to record a plus or a minus, all right? And so you would have something like minus 32,000, I think that's 768, up to 32,767 would be a 2-byte integer. Okay, so that's how integers are stored as binary numbers. Okay, characters and strings are stored as follows. A character is stored in a table. Okay, so there's basically a set of numbers where they say we're going to pick a certain number of bytes. The original table was called an ASCII table, ASCII table. Okay, and it only had 128 numbers. Okay, which was 1 byte. Okay, that was the original. And so the original capital A was 0, 1. You don't need to remember, what capital A was, but I'm just giving you an example. 0, 0, 1. That was a capital A. Okay, and it's just some table where we say that would be A, and then B would, if I remember, this would be, 1, 0. That would be B. All right, etc. So there's just some way of doing this. So there's certain, depending on how many zeros and ones you have, as how big your table is. Nowadays, this wasn't the old way, the ASCII table. Nowadays they have what's called Unicode. So if you ever hear about Unicode, Unicode's a lot bigger. I don't think I wrote in my notes how many bytes it is. You can go look that up. I think it was 4 bytes, if I remember right. Someone can look that up and tell me if I'm right or wrong. If it's 4 bytes. But now the table is called Unicode, and what that allows you to do is have a lot more characters that you can store. So you can have emojis, all right, if you have Unicode. You can store those things in a table. And a string is basically just a sequence of characters. Okay, so a single character would be stored by 1 byte, and then you'd have a sequence of characters so you could build up A, B. All right. The last one is floats or decimals. Okay, and the reason we need to be able to store floats or decimals is that if you remember, we looked back up here to integers and we were limited to this range. And we'd like to be able to use, we don't always need to store the exact number out to integer values, right? We might want to have something that can store decimals. And so the way to think about these guys is that they're stored as scientific notation. Okay. So what you would do is if I wanted to store pi, okay, I would say it's 3.14159, etc. I would store that as 0.314159 times 10 to the negative 1. And I would use some bytes to store this part, which is called the mantissa. Okay, some bit here for the sign. So this is a positive or negative. In this case, it's positive. And then some bytes to store the exponent. Okay, and so each of these numbers are stored in this way. So then you get, some zeros and ones to just store this part the same way as we do an integer. So we do this as a, binary to decimal conversion. And a binary to decimal conversion on that guy too. Well, I'll go back and fix that. Binary decimal on both of those guys. All right. And so a typical float is 4 bytes. Okay. And they divide some of the bit, 1 bit here, some of the bits here. Okay. And it can typically store 8 decimals of precision. Okay, and exponent of plus or minus about of 37. Okay, so I could do something like 6.02 times 10 to the 23rd. That would be good. Okay, but I could not do 6.02 times 10 to the 230. That I couldn't do, all right, because that's beyond that one. All right, and I could store 8 decimal points here, 8 numbers here, but I couldn't store 10, all right, for a float. Often, programs like Excel, we'll see, use what are called doubles, okay, which is 2 times the bytes of a float. Okay, and in this case, that means you get about 16 decimals of precision. Okay, and you get, where is it? About plus or minus 308 in terms of the exponent. Okay, so I've told you a lot of details here, some of which I don't really care that you know, and some of which I do care that you know. So the things that I don't care that you know the details, say, of 8 decimals or 16 decimals or the exponent, this sort of thing. But I care that you do understand that there are 4 different types of data, all right, and the basic idea of how they're stored. So as a single bit, as binary numbers, as a table, and as scientific notation. Okay, these are the things that I care about. All right, the last thing I'm going to tell you before our activity, all right, is part 3 is about finite precision errors. Okay, and finite precision errors, this is the consequence, okay, of only having 8 or 16 decimal points. Okay, so there's different kinds of errors that can come into play because we only have 8 or 16 decimal points. And I'm just going to give you some examples of these errors, and then in your homework you're going to play around with Excel and Python and see what some of the consequences of this are. Okay, so here are 5 examples. Ooh, that was like the worst 5 of all time. 5 examples, okay, of errors. And this is just to give you some examples of the kinds of errors here. So one is called truncation error. Okay, so truncation error is if I want to store 2/3, that equals 0.6 repeated infinitely. Okay, but I can only store that as something like 0.666 times 10 to the 0, right? And so, I have error by not being able to store all those other 6's. I have what's called an underflow error. Okay, that's if I try and represent 5.4 times 10 to the negative 400, my computer is just going to call that 0. Okay? Now that's a really small number, but maybe I happen to care about that level of precision, and I just now lose all of that, right? Because I can only have maybe 308. Okay, that's an underflow. An overflow is the opposite. Okay, an overflow is if I'm trying to store, let's say 3.8 times 10 to the positive 400. Okay, that's going to evaluate as an infinite value. All right, that's going to be a real problem in a computer. Both overflows and underflows can be a problem, but that's especially a problem with overflows. It'll usually do crazy things. So for instance, suppose you divide by a number that's really small. Now it'll give you infinity, because there's a 0 in the denominator. Or suppose you're trying to multiply by anything with infinity. That'll give you, infinity. That'll be a real problem. Okay. The last one is, I guess, I called these two different ones, but we'll see. This is round off error. Round off error. Okay, round off error comes in two flavors from addition. So this is our first one. So in addition, if I have 0.4300 times 10 to the 4th and 0.1 times 10 to the 0, I'm now going to add these numbers together. So if I go to do that, what I need to do is shift this piece over and add to the exponent. So I'm going to do 0.4300 times 10 to the 4th and 0.00001 times 10 to the 4th, right? Is that right? Let's see, 0.1, I have to move it 1, 2, 3, 4. Yeah, that's right. I had to move it 4 over. Okay? Now suppose I only had 4 decimals of precision. When I go to add that, that's going to give me 0.4300 times 10 to the 4th, because I can't store that one. So when I go to do addition with floating point numbers, I have to shift my mantissa to make the exponents line up to do addition. And, now I said I had 8. I don't want to have to write out all those zeros. But, if I had 8 decimals of precision, this would be fine. But if I only have 4 decimals of precision, this isn't going to work, and I'm going to get that round off error. Okay? A similar thing happens with subtraction. So round off error from subtraction is the same kind of idea. So suppose I have 0.4300 times 10 to the 4th, and I want to subtract 0.4290 times 10 to the 4th. So what's going to happen? So I'm going to get 0.0010 times 10 to the 4th, and now I'm going to represent that. I want to move and lose those zeros. I don't have to just store those garbage zeros. So I'm going to store 0.10, I don't know, times 10 to the 2, right? Because I lost 2 decimals of precision there. So these other numbers right here, they're now made up. They just come from random junk on the computer. And so now if I go to use that, I've lost that precision, okay? So round off error from addition and subtraction can mean I can add small numbers and nothing adds to it if I add a small number to a big. Or if I subtract a big number from another big number that's really close to it, I can lose precision. Okay? So that's the basic idea of error. And there are a couple examples to work through in an activity. And this is going to be the end of the lecture, so I'll go ahead and close. But there's an activity here that helps you explore data types and finite precision, okay, in Python. Okay, now data types and finite precision are also at play in Excel, and you'll also explore that on your homework. Okay, that's all I have time for. Have a great one, guys.